Well, it's a great pleasure to me to introduce Giovanni Bazzoni. He's from Università, degli Studi, dell'Insubria, and today he'll speak about symmetric and skewsymmetric complex structures. Thank you very much, Giovanni, for accepting this invitation.
Well, it's my pleasure, Romina, and I'm not seeing your faces now because now I see my presentation, but I know you're there, and I'm very happy to give this talk and to be at least online in Córdoba. It's a place that I had the chance to visit. We were remembering with Adrian 3.5 years ago, and it was very nice, and I hope I can visit you soon in the near future. The idea of this talk is to study some compatibility conditions when you have a manifold with a symplectic form and a complex structure. And the idea is to see what kind of geometry one can obtain, and how the geometric structures which arise, their multiplicity, because there are many things that one can say in the presence of these structures. Okay, so I will talk about symmetric complex structures. I will give a precise definition. And to obtain examples, as many of us do, I will consider Lie algebras and Lie groups. And then I will say a little bit about skewsymmetric complex structures. And I will say something about how one can combine those to obtain further geometry. So let's start with the notion of symmetric complex structure. Suppose you have a complex manifold. So I think of a complex manifold as a manifold with an integrable almost complex structure, J, which by the famous Nylander-Nirenberg theorem is equivalent to having holomorphic charts. So what is a complex symplectic structure on M? This is just sigma. It's a 2-0 form. So you decompose the complexified two forms using J, and then you have the 2-0 forms, which can be thought of, or actually are, the holomorphic two forms. And the sigma should be closed. So d sigma is 0 and also non-degenerate. So it's a complex 2-0 form, which is actually holomorphic, closed, and non-degenerate. So the first thing that one notices is that in this case, the holomorphic tangent bundle of M has even rank because it's a symplectic vector space. So the complex dimension of the manifold has to be even, and the real dimension has to be a multiple of 4. The second thing is that if you call n, so if the complex dimension of M is 2n, then if you elevate sigma if you wedge sigma with itself n times, you obtain an over-vanishing section of the canonical bundle of this complex manifold. So these manifolds are in particular examples of manifolds with trivial canonical bundle. What are the first examples that one can come up with? Well, if you have any complex manifold Mj and you take the cotangent bundle, pretty much as it happens for the cotangent bundle to any manifold, this cotangent bundle to any complex manifold has a canonical complex symplectic structure, which is constructed just formally in the same way in which one constructs the canonical complex structure, symplectic structure on the cotangent bundle of any manifold. Another construction that one can perform in this setting is that of a complex Lie group. And if you take any coadjoint orbit, then you have a complex symplectic structure on those. So this is parallel to what happens for coadjoint orbits of any Lie group. These are symplectic manifolds. And another setting in which complex symplectic structures appear is whenever you have a hyperkähler structure on a manifold. So I think of a hyperkähler structure as a three complex structures, I, J, and K, and some metric with respect to which I, J, and K are isometries. And you cook from those two forms, sigma I, sigma J, and sigma K, which turn out to be closed. And if you fix, for example, complex structure I, and you take the complex 2 form sigma J plus I sigma K, which turns out to be holomorphic with respect to I, this is a complex symplectic structure. So although not in a canonical way, every hyperkähler structure induces a complex symplectic structure. Okay, So hyperkähler is a special case of complex symplectic structure. We'll come back to this in a little bit. So it turns out that it's very easy to prove that if you have a complex manifold, then the set of all complex symplectic structures on M is in bijection with the set of real two forms. So now it's not omega is not complex, it's just any two form, which is symplectic, of course, so it has to be closed and non-degenerate. And moreover, there is a compatibility condition between J and omega. So omega of J x y has to be omega x J y for every x and y vector fields on M. This is just, it's very simple, it's basically linear algebra. And so you define a, in presence of a complex manifold Mj with a symplectic for omega, you call J symmetric with respect to omega if the condition above is actually satisfied for every pair of vector fields x, y. Okay, so this is reminiscent of symmetric endomorphisms with respect to a inner product on a vector space. This is why I call them symmetric. And by using the above proposition and this definition, turns out that a complex symplectic structure on M is actually equivalent to a pair J omega, where J is symmetric with respect to omega. Okay, and this is why we care about symmetric complex structures. So we can think of them as another disguised way for considering complex symplectic structures. Okay. Let's see how we can obtain examples of such structures on compact manifolds by first considering structures on Lie algebras and Lie groups. Okay, this is very standard. So if you have a real 2n-dimensional Lie algebra, a complex structure on it is just pretty much as it happens on every, pretty much as one does for manifolds. A complex structure is just an endomorphism of G, which squares to minus the identity and with vanishing Nijenhuis tensor. This is so the first part is just almost complex structure, and the second one is the integrability condition. And a symplectic structure on G is just a 2 cocycle, so an element of the second exterior power of G star, which is closed. So this D now stands for the Chevalier-Alembert differential. And if n is half of the dimension of the Lie algebra, then n omega wedged with itself n times is non-zero. And by mimicking what we did for like manifolds, we define a complex symplectic structure on a Lie algebra, just on a Lie algebra G, just as a pair J omega, where we have a complex structure J, a symplectic structure omega, and we require J to be symmetric with respect to omega. So whenever you pick vectors x and y in G, then you have omega of J of x y equal to omega of x J y. Okay, so we think of complex symplectic structures on Lie algebras as complex structures which are symmetric with respect to J, with respect to omega. Of course, we could also have a completely equivalent definition with 2 zero forms on G. But we prefer to work with this sort of in this setting, so to say. And notice that pretty much as happened for manifolds, the complex dimension of a complex symplectic Lie algebra is even. So these Lie algebras have dimensions as real Lie algebras, which are multiples of 4. We focus on nilpotent and solvable Lie algebras. Why? Because, for example, if you think of simple Lie algebras, they usually give rise to compact Lie groups, and usually these compact Lie groups have B2 equal to 0, so they will not likely have symplectic structures in general. So the realm in which one usually studies these structures is that of nilpotent and solvable Lie algebras. So consider any Lie algebra G and define the so-called ascending central series by setting G0 equal to 0, so the sort of trivial subspace. And for any k greater than or equal to 1, define GK to consist of these vectors X, so that whenever you multiply, so you bracket them with all elements in G, you fall back into GK minus 1. So this is an inductive definition, and it's easy to see that every GK, well, that GK is contained in GK plus 1, and that each GK is an ideal inside GK plus 1. And by the very definition, G1 is just the center of the Lie algebra, just by definition. And you call Lie algebra nilpotent if you can find some M, some integer M, such that positive integer M, such that eventually this ascending series fills up all G. Okay, and when you pick the smallest M, which fulfills this condition, you call this the nilpotency step. So, for instance, if you think of M equal to 1, so nilpotency step 1, this is just abelian Lie algebras, because this is saying that G1 is G, but G1 is the center, so every element is central, so the Lie algebra is abelian. So nilpotent is a generalization in some sense of abelian Lie algebras. And usually I will use the shorthand notation NLA for nilpotent Lie algebra, just to make the notation more compact. And we'll also care a little bit about solvable Lie algebras, not as much as we'll care about nilpotent Lie algebras. And in this setting, just let me define a solvable Lie algebra as a Lie algebra whose commutator subgroup or ideal is actually nilpotent. Okay, this is not the standard definition, but it's equivalent to the one, to the usual one, also given in terms of some ascending series. So the first piece of result I would like to present to you is a classification of four-dimensional complex symplectic Lie algebras, which we obtained. So notice that there is a theorem saying that if you have a four-dimensional, that's important, symplectic Lie algebra, then the Lie algebra is automatically solvable. So that's why we care so much, especially in dimension 4, only about solvable, or more specifically, nilpotent. So this theorem says that if you have any G, J, omega, then G is constrained to be one of these 5 Lie algebras, and J has to be one of these specific complex structures, and also omega is almost fixed. So in the first 4 cases, there is just one symplectic structure, and in the last case, there is a one-parameter family, so indexed by or parameterized by S1, by the real projective line. So the first 2 Lie algebras turn out to be nilpotent, while R4 is, of course, abelian, and RH3 is the Kodaira-Thurston algebra, Lie algebra. So it's the sum of the Heisenberg algebra with a trivial factor. Okay, and these 3 Lie algebras are solvable, non-nilpotent. We don't care that much about them, at least with an eye toward compact examples, because these 3 Lie algebras are not unimodular. And there is a necessary condition given by Milner, which says that if some Lie algebra or some Lie group is to admit compact quotients, then the Lie algebra has to be unimodular. So basically, the volume form is not allowed to be exact. Okay, so the only Lie algebras which may give rise to compact examples are the first and the second. Okay, and this theorem is actually not hard, because there was a classification of complex structures on 4-dimensional Lie algebras given by Gabriele Ovando, and there was also a classification, or at least a listing, of all possible symplectic forms omega. So what we did was just imposing the symmetry condition of J with respect to omega, and then there was last step, which was actually finding a normal form. Okay, so this is a complete classification in dimension 4. We have just 5 examples. 2 of them are unimodular and nilpotent, and 3 of them are not, neither nor, are solvable, and they don't have compact quotients.
So Giovanni,
yes.
So you are saying that on each Lie algebra there is only one pair.
Exactly.
Up to,
well, I mean, the last one has more, but it's indexed by, so it's a moduli. So this is just one point.
Which one?
So, for example, R4 has just this one, and R2 prime has just this complex structure with this, exactly this symplectic form, meaning that any other is symplectomorphic to that one.
Up to
isomorphism, which fixes the complex structure.
But with automorphism, right?
Yeah. With automorphism, yeah.
Okay.
So what we did was we sort of guessed automorphisms which fix the complex structure, and we played with them to bring the general Tuco cycle to a standard form.
Okay. Thank you.
Thanks. So let me now describe ways to construct and deconstruct complex symplectic Lie algebras. So our aim is always that of obtaining examples, right? So let me start with the general setting of a symplectic Lie algebra, okay? So G omega. An ideal A is isotropic if whenever you pick vectors x, y, and A and you compute the symplectic form on them, this is 0, okay? And in this case, one can show quite easily, actually, that if you take the quotient G bar, which is the symplectic orthogonal of A quotiented by A, then omega induces a symplectic form omega bar on it. And we call G bar omega bar the symplectic reduction of G omega with respect to this isotropic ideal. Okay, this is basically mimicking symplectic reduction in symplectic geometry. Okay, and what we did was to extend, or actually the other way around, specialize this construction to complex symplectic Lie algebras. So in this case, you need an ideal A which is not only isotropic, so not only omega restricted to it has to vanish, but also J invariant. Well, in that case, J omega induces a complex symplectic structure J bar omega bar on the same quotient, so on the quotient of the orthogonal of A with respect to omega by divided by A. Okay, so you can not only reduce, you can do reduction also in the complex symplectic setting.
Sorry, Giovanni, who is FLM? Maybe you.
Oh, okay. Sorry, I would have said that at the end, but it's myself, Marco Freibert, Adela Latorre, and Benedict Meinke. And there was also another portion here. I should have said that, of course. I would have said that at the end, but it's a good point to say it now. This is again myself. This is Alejandro Gil Garcia, who is now a PhD student, and this is again Adela Latorre. Okay, I'm sorry. I should have said that at the beginning. Thank you. And this is. We call this G bar, J bar, omega bar, the complex symplectic reduction of J omega with respect to the ideal. Okay, so reducing means basically going down the dimension. And now we show that we can also invert this construction. And since in chemistry, oxidation inverts reduction, we're not the first ones, but we call this construction complex symplectic oxidation. So I don't want to enter in details because it's quite involved. It's not difficult, but it's quite involved. Out of a complex symplectic Lie algebra, G bar, J bar, omega bar of dimension 4n, recall that the real dimension, this is the real dimension, has to be a multiple 4, and some what we call oxidation data, which are some tensors on G bar, which have some compatibility conditions with J bar and omega bar. I don't want to say too much. It's, as I said, quite involved, but it's not difficult. There is a construction which we call complex symplectic oxidation, which gives back to you a complex symplectic Lie algebra G, J, omega of dimension 4n plus 4. So the dimension goes up, okay, of exactly 4 dimension, of just, that's the smallest possible gap, right? Because the dimensions have to be multiples of 4. So if you're in 4n, the next in higher dimension has to be 4n plus 4, okay? And by construction, this oxidation contains a 2-dimensional isotropic J invariant ideal A. So you are in the position of reducing G, J, omega with respect to this ideal A, and as one would hope at least, the reduction of G, J, omega with respect to this ideal gives again G bar, J bar, omega bar. Okay, so in this sense, a reduction inverts oxidation. Okay, so you can oxidate, you go up 4 dimensions, and then you come back by quotienting exactly with respect to this sort of canonical, so to say, 2-dimensional isotropic J invariant ideal A, which is produced by oxidation. Let me try this. This was very general, so this can be done in general for any complex symplectic Lie algebra. let me try to say something more about nilpotent Lie algebras, which are the main topic, or one of the main point of interest. So if you have a nilpotent Lie algebra with a complex structure, up here there is no compatibility between J, so the complex structure, and this ascending central series, which defines the nilpotency of G. So an idea would be to see if you can mix the two things. So if you can impose to this ascending central series to be adapted to J. So you fix a complex structure J on a nilpotent Lie algebra, and you define its adapted ascending central series by starting with 0. So G0 of J is just 0, and you do the same inductively. So Gk of J is the vectors, which when you bracket them with all the vectors in G, you fall again in Gk minus 1 of J, but not only them, also J of them. Okay, so J of X is also, when bracketed with G, goes back to Gk minus 1 of J. That's for every k bigger than or equal to 1. So for instance, G1 of J is the largest J invariant subspace in the center. Okay. Well, the thing is that this could have some relation with the ascending central series or not. Okay. So that gives a way of distinguishing complex structures on a nilpotent Lie algebra. So if you're given that, a nilpotent Lie algebra with a complex structure, you call J quasi-nilpotent if this adapted ascending central series starts. So if G1 of J is non-zero, okay? It doesn't need to, but if it's different from 0, then you call the complex structure quasi-nilpotent, and you actually call it nilpotent if there exists a P such that after iterating this construction P times, you actually obtain again the whole Lie algebra, and you call it weakly non-nilpotent if there is a P such that this adapted ascending central series stabilizes. It reaches some GP of J, which is not G, but then stabilizes. Okay, that's weakly non-nilpotent. And if this adapted ascending central series doesn't even start, so if G1 of J is 0, then you call the complex structure strongly non-nilpotent. Okay. So this is you have to live with this. Okay, sometimes you're not going to be able to find an adapted ascending central series. And what is very relevant is that if you have a nilpotent Lie algebra with a quasi-nilpotent complex structure J, then there is a construction which tells you that this GJ, this pair, is actually I don't want to enter details, but it's some kind of complex extension of a nilpotent Lie algebra G tilde of lower dimension with a complex structure J tilde. So basically, GJ is some kind of extension of G tilde J tilde. Whereas the complex structures, there is a typo here. The complex structures which are new to each dimension are exactly those of strongly non-nilpotent type, okay? Because they cannot be basically reduced, or respectively, the complex Lie algebra with complex structure cannot be obtained by extending something in lower dimension, okay? So these are those who are new to each dimension, so to say. And this definition is due separately to Cordero, Fernandez, Gray, Ugarte, and also more recently to La Torre, Ugarte, and Villacampa. So a first result, which concerns complex symplectic structures on nilpotent Lie algebras in dimension 8, is that if you have such an example, so if you have, well, such a datum, so an 8-dimensional complex nilpotent Lie algebra, and you know that the complex structure is strongly non-nilpotent, then there is no complex symplectic structure on GJ. Okay, so you won't be able to find any omega with respect to which J is symmetric. Okay, that's our result, and this result is actually a little sad in some sense, and I'll tell you more why. Because we have to actually use a classification result of 8-dimensional nilpotent Lie algebras with strongly non-nilpotent complex structures obtained recently by La Torre, Ugarte, and Villacampa. Okay, so two questions arise. The first one is it possible to prove this directly, so without appealing to the classification? And the second question is this specific to dimension 8? Could you have some 12-dimensional nilpotent Lie algebra with a strongly non-nilpotent complex structure which still admits complex symplectic structures? We don't know. And it's not so easy because you have to come up with something that does not, which actually lives in dimension 12, does not come from lower dimension. So it's kind of hard. No? You have to think of some complex structure and see that it's strongly nilpotent and see that it does have complex symplectic structures. So these are two questions.
Giovanni, one question. An abelian complex structure is nilpotent, quasi-nilpotent? Does it have some relation with this?
I don't remember, because abelian is that j of x, j of y is xy, right?
Yes.
Let me think. I'm not sure. I'm not sure. I don't want to say anything because I'm not so sure. I mean, it would make sense, but let me think. If you have j of x, j of y.
Okay. Yes.
I don't know. I don't know.
Maybe they're probably nilpotent, but I don't know.
Yeah, it would make sense. It would make sense, but you got me. I don't know. Okay, sorry.
Okay, thank you.
You're welcome. So
I mean, abelian seems to be always quasi-nilpotent, right?
Yeah, I guess that would make sense. So
because if x is in the center, then jx.
Yeah, because if you have it makes sense. It makes sense. Okay, sorry, there is some bug flying around me. Okay, so the upshot for us is this: if you have an 8-dimensional complex symplectic nilpotent Lie algebra, you can reduce it to dimension 4. Okay, and how do you do that? I do it because it's very simple. Well, the first thing you have to observe is that if you reduce a nilpotent Lie algebra, so if you quotient basically a nilpotent Lie algebra by something, you're again nilpotent. And if you start with some 8-dimensional complex symplectic nilpotent Lie algebra, then you know by our previous theorem that J is quasi-nilpotent. So you just pick some x in J1. Well, actually, you can pick some x in the center, so to say, and then J of x is also in G1 of J. So I should have written better. G1 of J is non-empty because you can find an x in the center, and J of x is also in the center because J is quasi-nilpotent. And then basically you see that the ideal generated by x and J of x is actually not only J invariant, of course, but also isotropic. Okay, the first equality. So this equality comes from the symmetry of J with respect to omega, and this comes from the fact that omega is a 2-form. So when you switch the arguments, the sign has to change, and this leaves no choice but omega x of J of x being 0. So it's very simple. Okay, so we can reduce every 8-dimensional complex symplectic nilpotent Lie algebra to 4 dimensions. Okay, and remember, in 4 dimensions we have a classification. We have a very precise classification of nilpotent Lie algebras. So basically, you can oxidate those. You can oxidate them again. So remember, I told you at the very beginning that there are just 2 nilpotent Lie algebras which admit complex symplectic structures, basically R4 and Kodaira-Thurston. And in general, that's very general, not just in dimension 4. If you have a complex symplectic nilpotent Lie algebra, G bar, J bar, omega bar, and you choose the oxidation data so that the resulting Lie algebra is nilpotent, then J is actually quasi-nilpotent. Okay, so you produce something that can be reduced. Okay, and it is also a fact that every complex symplectic nilpotent Lie algebra of dimension for n+4, where J is quasi-nilpotent, is actually the complex symplectic oxidation of a suitable complex symplectic nilpotent Lie algebra of dimension 4 less. Okay, so this says that every 8-dimensional complex symplectic nilpotent Lie algebra can be obtained by suitably oxidating 4-dimensional complex symplectic nilpotent Lie algebras. Okay, so all of them can be obtained that way. We actually determined all the possible oxidation data. So in principle, we do have a classification, but it's very hard to tell whether this data produce isomorphic Lie algebras. So we don't know that. So we have a list, but we don't know that the list is non-redundant. Okay, so that would be an interesting question to see if one can classify this 8-dimensional nilpotent Lie algebras with complex symplectic structures. Recall that there is no classification of 8-dimensional nilpotent Lie algebras, right? So it's not possible just to check a list and and see what happens. And as a byproduct of our analysis, we see that the nilpotency step of such an adimensional nilpotent Lie algebra with a complex symplectic structure is at most 4. Okay, so this says that the presence of a complex symplectic structure in a dimension constrains or sort of puts a limit to the length of the ascending central series. Okay, it could be 7 in principle in dimension 8, but if you have a complex symplectic structure, you are actually you are at most 4. Okay, and we don't know what happens in higher dimension. So we don't know if, for example, in dimension 12, the nilpotency step is at most 6 or something like that. We have no idea. Okay. Of course, the reduction, so you can reduce only if you have a suitable ideal, which has to be J invariant and isotropic. So we don't even know if you can reduce everything. So we don't know what happens starting in dimension 12. Okay.
Giovanni.
Yes.
About the proposition.
Yes.
Is that true because any term in the ascending central series is even dimensional?
I don't remember exactly, but I don't think so. No, I should go to the paper, but I don't think so.
No, that's not true.
No,
every term is dimension.
No. I don't remember exactly everything that happens, but I don't have this feeling. No.
Okay.
Thank you. So now we know a lot about these structures on nilpotent Lie algebras. Let's see how to obtain compact manifolds. I mean, you all know this, but let me just go quickly through it. A Lie group which is connected and simply connected is called nilpotent if its Lie algebra is nilpotent, with the definition that I gave before. And once you have a nilpotent, so connected and simply connected nilpotent Lie group, you can quotient it by a lattice gamma, which is a discrete and co-compact subgroup, and the quotient is a Nil manifold by definition. Okay, so the prototypic example is that of G abelian Rn, and you quotient by z to the n by obtaining a torus. Okay, so a torus is the easiest example of a Nil manifold. Okay, and there is a very successful criterion to say when a connected and simply connected nilpotent Lie group admits a lattice, and this happens exactly when G has a rational structure. So when G, which is a real Lie algebra, is actually obtained by extending coefficients to a rational Lie algebra. So one says that G has a rational form or a rational structure. And this is very nice. And if you just compare it with what you may want to call solved manifolds, so quotients of solvable Lie groups by lattices, there is no such a theorem. So a piece of art in the theory of solved manifolds is actually to come up with a lattice, okay, or prove that no lattice exists. So it's much harder. But for Nil manifolds, we are very lucky. This is due to Malchev, this proposition that I'm quoting here. So suppose you have a Nil manifold. Whenever you have a tensor, so you think of G as the fractional G as the tangent space in the identity element of the Lie group. And whenever you have a tensor defined on G, then you have a left invariant tensor on the Lie group. And since you quotient on the left G to obtain a Nil manifold, then you have tensors on N. Okay. And for example, we can apply this to differential forms. And we have an injective inclusion of cochain complexes. So the so-called Chevalier-Allenberg complex, so to say differential forms on the Lie algebra, is included into the differential forms on the Nil manifold. And the very remarkable result of Nomithu says that this inclusion of cochain complexes actually induces an isomorphism in cohomology. Okay, so we can compute the cohomology of Nil manifolds just by computing Lie algebra cohomology. Okay, and another result that I'm quoting here now is a very remarkable result by Benson, Gardner, and Hasegawa. So 2 different proofs in pretty much the same time, which a Nil manifold endowed with a killer structure is automatically diffeomorphic to a torus. So, for example, we saw before that if you have a Nil manifold in dimension 8, well, let's say, let me step back to nilpotent Lie algebra. So nilpotent Lie algebra in dimension 8 with a complex symplectic structure has nilpotency step at most 4. This theorem is saying that if you have a nilpotent Lie algebra, this theorem together with the Nomisto theorem, if you have a nilpotent Lie algebra and you know that it admits a Kähler structure, then the Lie algebra is abelian. Okay, so the philosophy or the leitmotif is that the more complicated your Lie algebra is, the less you have geometric structures. Okay, so for example, Kähler structure on nilpotent Lie algebras only exists if the Lie algebra is abelian. Okay, and this is why this theorem is important. Let's use our Lie algebras to construct a-dimensional complex symplectic nil manifolds. So if you have some geometric structure on a nil manifold, which is defined by a left invariant tensor on the corresponding Lie group, then you call those structures, well, it's just terminology, you call them left invariant. And of course, if you have a complex symplectic nilpotent Lie algebra, you determine a left invariant complex symplectic structure on the only simply connected nilpotent Lie group with Lie algebra G. And then if you have a rational structure on the Lie algebra, you have a lattice in G, you can quotient, you can obtain a nil manifold, and this nil manifold has a complex symplectic structure. Okay, so you know precisely what to do. You just take the complex symplectic structure on your Lie algebra and you push it down. First push it up to the Lie group and then down to the nil manifold. Okay, so the idea is that we can use our study of a-dimensional complex symplectic nilpotent Lie algebras to obtain examples of a-dimensional, let's say, nil manifolds which admit complex symplectic structures. Okay, and we have a lot of them. Okay, and to make a connection with what I said in the beginning is that you have many complex symplectic nil manifolds. I don't say what many means, but actually a lot. And these nil manifolds admit no hyperkähler metric. Why? Well, because of Benson, Gardner, and Asagawa. Because if they admitted a hyperkähler metric, they would also admit a Kähler metric, because hyperkähler is a very special instance of Kähler. And so the Lie algebra should be abelian. But we do know, well, I didn't tell you precisely, but we do know that the nilpotency step of a Lie algebra in dimension 8 with complex symplectic structure is at most 4, but actually all these nilpotency steps are actually covered. Okay, so for example, you have 3-step nilpotent Lie algebra with complex symplectic structure, and this admits no hyperkähler metric. Okay, so in the beginning, I told you that every hyperkähler metric determines a complex symplectic structure, but that's very far away from the converse. Okay, complex symplectic structure is flexible and hyperkähler is very rigid. Okay, so in this way, we can obtain many examples. Let me just say very quickly that in the paper with Marco, Adela, and Benedict, we also consider relations of complex symplectic structures with, for example, hypercomplex structures, which is another kind of geometric structure which lives in real dimension multiple of 4. And this can also be related in a very nice way, or at least it can be not related, but one can study if this structure can coexist on a manifold, and we can use our construction also to construct, for example, manifolds which are hypercomplex but not complex symplectic, or complex symplectic but not hypercomplex. Okay, so you can use these examples pretty much at level of Lie algebras to answer many questions on the existence of structures on manifolds. Okay, as one usually does with nil manifolds. What I would like to do now is to say something very short about skewsymmetric complex structures, just a couple of slides, and then what we can do when we try to combine those two. Okay, so symmetric and skewsymmetric. If you have a complex manifold Mj, a pseudo-Kähler structure on M is a two form of type 1-1. So again, you decompose your two forms using J, and there exist the forms of type 1-1, and omega has to be there to call it pseudo-Kähler, and it also has to be closed and non-degenerate. Okay. In this case, so whenever you have a pseudo-Kähler structure, you can define a symmetric tensor by this formula, and actually it's not degenerate because omega is, and that's a pseudo-Riemannian metric. It's pretty much like Kähler, so pseudo-Kähler encompasses Kähler. But it doesn't need to be positive definite. This positive definitiveness of G is related to the fact that J is tamed by omega, which is not necessarily true. Okay. So what does it mean to be omega 1, 1? Well, basically, it means that what does it mean? Sorry, for omega to be in omega 1, for little omega to be in big omega 1, 1. Well, it basically, if you spell out this condition, means that J is skew-symmetric with respect to omega. Okay, so if we have, according to what I say in this definition, if you have a complex manifold Mj and you have a symplectic form on M, you call J skew-symmetric with respect to omega. If whenever you pick x and y, then you have that omega of jxy is minus omega of xjy. It's pretty much like symmetric, but with the minus sign, reminiscent of skew-symmetric or skew-adjoint endomorphisms with respect to inner products on vector spaces or manifolds. Okay, so by spelling out what it means to be in big omega 1, 1, you see that actually a pseudo-Kähler structure on M is equivalent to a pair J omega, where J is skew-symmetric with respect to omega. Okay, so of course it's a pair J omega, where J is a complex structure and omega is a symplectic structure, and J is skew-symmetric. Okay, so we have these two cases, because also omega 2, the complexification of omega 2 of the two forms is splits as omega 2, 0 plus omega 1, 1 plus omega 0, 2, which is conjugate to omega 2, 0. So basically, either you're symmetric or you're skew-symmetric or you're mixed. Okay, but the pure classes are in some sense symmetric and skew-symmetric. Okay, this is what makes the whole story nice to me, at least. What can you do once you have both structures? Well, you can combine them, and we consider a sort of structures on a complex manifold, which is a special case of both, so to say, the symmetric and the skew-symmetric setting. Okay, let me give this definition. A hypersymplectic structure on a 4n dimensional manifold, 4n is the real dimension, consists of a complex structure J, so we know what that is, a product structure E, so E is also an endomorphism of the tangent bundle, which actually squares to plus identity. We don't want it to be plus or minus the identity, because that would be maybe a bit too simple. And also, E satisfies some integrability condition very similar to the one satisfied by J. So this vanishing of this Nichen, who is tensor, can also be written down for E. We have more. We have a metric. And we also have that E and J anti-commute. So EJ is equal to minus JE. G has split signature, so if the manifold is 4n dimensional, real, then the signature of G is 2n to n, so 2n positive, so to say, directions, and 2n negative directions, so to say. And also there is a strong compatibility condition between J, E, and G. So G of x, y is equal to G, J of x, J of y, and is also equal to minus G of E of x, E of y for every pair of vector fields. Okay, so this is the compatibility between signature, skew-symmetry, and compatibility with the metric. And these kind of metrics they can be thought of as, they sometimes called para-Hyper-Kähler, but I don't really like the para thing, because then I forget what it means. They are basically the relatives of Hyper-Kähler metrics when the signature is neutral, so when it's split. Okay. Their holonomy is contained in sp2nr, contained in turn in sp2nc, and sp2nr is one of the two real forms of sp2nc. The other one is spn, which is actually the holonomy group of Hyper-Kähler geometry. Okay, so even from this point of view, you have this group sp2nc, which, by the way, is the structure group of a complex symplectic structure on a manifold, when one thinks of geometric structures as defined by reductions of the tangent bundle, so as G structures. And so in this sense, holonomy tells us that these are related to Hyper-Kähler metrics. They were introduced by Hitchin, I don't know when, maybe in the 90s, I think. And they are neutral, so the signature to n. They are Ricci flat, and moreover, they are Calabi-Yau. Okay, so here Calabi-Yau refers to, as a complex manifold, Mj has trivial canonical bundle. Okay, so they are interesting from many points of view. They're also relevant in physics and so on. They are the relative of Hyper-Kähler metrics in split signature, in the neutral case. what is the relation with symmetric and skewsymmetric complex structures? Well, suppose you have a hypersymplectic structure, JEG on M, and you can define two forms, omega pk of xy by the first formula and omega cs xy by the second formula for every vector field x and y. And of course, pk means pseudokiller and cs means complex symplectic, because in fact, turns out that both omega pk and omega cs are closed and non-degenerate. J is skew-symmetric with respect to omega pk, so omega pk is what we think of as we can think of it as a pseudokiller form, and also J is symmetric with respect to omega cs, so omega cs is actually complex symplectic. So in a natural way, a hypersymplectic manifold is both pseudokiller, skew-symmetric, J is skew-symmetric, and complex symplectic, so J is symmetric with respect to convenient symplectic forms. Okay, so it's an instance in which symmetric and skew-symmetric are combined. Okay, that's what I meant in the beginning of this section. So suppose you start with something different. You try to reverse your path. Okay, suppose you have a complex manifold Mj, and you know that J is symmetric with respect to some two form omega cs, and is also skew-symmetric with respect to, so you have a fixed complex structure, which is symmetric with respect to omega cs and skew-symmetric with respect to omega pk. Okay, and you know that omega cs and omega pk are both closed and degenerate. So J omega cs is complex symplectic and J omega pk is pseudokiller. Since they're non-degenerate, both omega cs and omega pk actually define vector bundle isomorphisms from Tm, from the tangent bundle to the cotangent bundle. So you can compose them, you can invert them and compose them, and you call E the composition between omega pk to the -1 seen as an endomorphism, and as an isomorphism, sorry, with omega cs. Okay, and also you have a natural pseudokiller metric, which is that of J omega pk. Okay, well, the theorem says that if E squares to the identity, so if it happens that E is what is called a anomalous product structure, you don't even have to check integrability. Okay, if this condition is fulfilled, then JEG is a hypersymplectic structure on M. Okay, so just by this small compatibility condition, so as soon as E squares to the identity, then you have a hypersymplectic structure. Okay, so this is a powerful way to construct examples. Okay, because you can start with this setting. You have a J, you have omega cs, you have omega pk. You check whether E defined this way squares to the identity, and if that's the case, then you're hypersymplectic. Okay, so for example, we can give an application to examples of compact manifolds, which of course will be nil manifolds, which admit or not hypersymplectic structures. As I say, these are nil manifolds, and the kind of structures we are interested in are left invariant geometric structures. Okay, so for instance, we have an A-dimensional manifold with two non-equivalent complex structures, J1 and J2, such that the first one admits hypersymplectic metrics, and the second one is neither symmetric nor skew-symmetric with respect to any symplectic form. So MJ1 is hypersymplectic, but MJ2 is not on the same manifold. Okay, so different complex structures can lead to very different behaviors. Okay, so this means that this bullet 2 means that you sort of check all the possible symplectic forms, and you find no symplectic form with respect to which J is symmetric, and no symplectic form with respect to which J2 is skew-symmetric. And another kind of result is that you also have another, well, similar but different. You have an A-dimensional manifold which has a complex structure, and you can find symplectic forms with respect to which omega is respectively symmetric. Sorry, J is respectively symmetric or skew-symmetric. Okay, but the manifold does not admit any hypersymplectic structure, left invariant. Okay, so this symmetry and skew-symmetry can coexist without giving rise to some hypersymplectic metric. Okay, so you have all different behaviors. And let me finish with a different application of this result, which is the following. So all known examples of nil manifolds with hypersymplectic metric have so the associated Lie algebra is at most 3-step nilpotent, up to my knowledge. So this is actually a result of or Adrian and Isabel constructed many of these examples on certain kinds of extensions of R to the 2n. So the question is, what about 4-step nilpotent? So remember this philosophy that the more you get away from abelian Lie algebras, the less you have structures in some sense. So for example, Kähler. And using our construction, we obtain 2 one-parameter families of hypersymplectic metrics on a nil manifold with n, which is h over lambda, and the Lie algebra is actually 4-step nilpotent. And if you remember, in dimension 8, the highest nilpotency step of a complex symplectic nilpotent Lie algebra was 4. So since hypersymplectic is in particular complex symplectic, that's also the highest nilpotency step for a hypersymplectic metric. Okay, and we prove that for every n greater than or equal to 2, you can find a 4n-dimensional nil manifold with 4-step nilpotent Lie algebra H, which admits 2 families, so 2 one-parameter families of hypersymplectic structures, which I call JC, so with respect to the same complex structure JC, E hat and G hat, and JC EG, where both metrics are complete, both metrics in the family, so each member of the family is complete. The first one is flat, and the second one is non-flat. For example, Adrian's and Isabel's examples, when the metric is flat, then the nilpotency step is actually 2. Okay, that's actually equivalent as far as I understood. So in nilpotency step 4, we have both flat and non-flat. Okay.
So, Giovanni.
Yes.
How do you prove that is indeed a curve, a genuine curve, by hand or using some?
Well, the trick here is that the input is always the complex structure. So we rely on results by Adela and Luis and Raquel, in which they write down non-equivalent families of complex structures. So we have this JC, and we prove that JC is biolomorphic to JC prime if and only if C is C prime. Okay.
Okay, so you use another result.
Yeah, well, we prove it in the paper. Okay, so our input is JC. Without JC, we couldn't start. Okay. So once you have JC, you basically go around and look for omega pk and omega cs, and then you play long enough till you find a metric which does the job. Okay, you compute a lot of Riemann tensors, and then you find your example. And these metrics, so these complex structures are biolomorphic if and only if C is equal to C prime. So in particular, the metrics so the hypersymplectic structures cannot be isometric. They could be just as Riemannian metrics or pseudo-Riemannian metrics, okay, but not as hypersymplectic metrics, okay?
Perfect, okay.
And actually, that was my last slide. So, gracias. And now comes my co-authors, which I forgot to mention at the beginning. Thank you very much.
Thank you very much for the beautiful talk. Is there any question? Any other question?
Yes, for the complex symplectic case, have you studied some related Hermitian metrics to these complex structures? Which kind of Hermitian metric can you obtain?
No, we haven't.
Maybe forgetting about the symplectic structure, because you have, in any case, you have a manifold with a trivial canonical bundle.
Yes, yes.
So it would be interesting.
We have not studied this. It would be very, very interesting. It's surprising that there is basically no study of complex symplectic structures, even on nilpotent algebras. So we were very surprised that.
Okay.
So, for example, we are now working on structures on, for example, almost abelian Lie algebras. Or your question was about abelian complex structures. What happens if your complex symplectic structure has an abelian J? So all these questions are open, but and of course that of the possible compatible metrics also. That's also
okay. And another question is, there were some known examples of compact complex symplectic manifolds.
Yes, there are.
Because I think that you mentioned only non-compact examples, maybe.
Yeah. No. Of course, the Kodaira-Thurston manifold is compact and has complex symplectic structures, for example. Okay. So what is very difficult and tricky to find, and I am aware of just one example, is so I cheated a little bit, because I say that I have many complex symplectic structures or manifolds which admit no hyperkähler metrics. Okay, but by general theory that if you have a hyperkähler metric, then the fundamental group has to be either trivial or very small. I don't remember. So B1 has to be 0, and nil manifolds never have B1 equal to 0. Okay. So let's say that we know that the metric is the holonomy is not even contained in SPN. I should have been more precise. What is not known, or what is just known in one example, is some complex symplectic simply connected manifold. That's very hard. And this is very surprising, because you have very few hyperkähler, and that's problematic, but it's very well known. But complex symplectic, you can start with lots of examples. And yet there is just one construction that I'm aware of, which is by one, which constructs, well, he calls them holomorphic symplectic, but construct complex symplectic manifolds with which are simply connected by doing some kind of Bouville construction, actually, to the Kodaira-Thurston manifold.
Okay.
And my idea would be to have all these examples, like on nil manifolds, and try to produce out of them some simply connected examples, for example, by orbifold constructions. But these singularities that you get by quotienting by some finite group to kill the fundamental group are almost impossible to actually resolve. So there are many papers by Bouville, by Verbitsky, which say this symplectic singularity, so complex symplectic singularity, cannot be resolved, and this one neither. So it's very hard. But one would think that there should be many, even simply connected. So I'm very puzzled by this. I don't understand why.
Okay, thank you.
Thank you.
Is there any question? Any other question? Well, if not, let's thank again Giovanni.
Thank you.